This is a PowerPoint presentation that I'm going to be discussing the databases that we've used in Soil Survey. And historically, the Soil Survey program has published soils information using a Soil Survey manuscript. And we sat down and we wrote everything that we needed, and we've developed our charts and inserted our interpretations and properties. But beginning in the late 60s and the early 70s, the NCSS Soil Science recognized that there was a need for automating this process to be able to get this soil survey information out the door a little bit quicker. So in more than 30 years since then, NCSS has been the leader in the adaptation of information technology. And as a result of this demand for soil survey information, the databases were developed and improved to the point of what we have now. And currently we have a position that a collection to publication database system that begins with NASAS and ends with Web Soil Survey. Of this, the objectives are to discuss the population, the analysis, and the publication of the soil data. And I want to give you a little bit of understanding on how the NASAS correlation concepts came about. And then finally, to identify the correlation procedures that we need to create a fully reversible correlation, and that has changed dramatically over the recent years. So let's start with the history of the database. Prior to 1972, just about all of the manuscripts were handwritten. So they were typed out, and the charts for the properties and interpretations, if there were any, were created and basically typed. In 1972, we created this concept. This is when we got into when we got into the database system at Iowa State. And they created what was called the soil interpretation record. The intent behind that was to develop these manuscript tables and have them computer generated. And I'll go into more details on that later. And then in '85, that soil survey interpretation record turned into the state soil survey database. And then in 1994 is when we began the release of NASAS. And then 2003 is when we created the staging server, the soil data warehouse, and the soil data mart and the Surgo database. The importance behind that is that now published our information as databases. And then in 2005 is when we created the Web Soil Survey, and then here we are in 2015. This is an example of one of the early soil survey interpretation records. And you'll notice that it's on a particular series, and this is the Cecil series, and it was in MLRA 136 in North Carolina. And you can see the authors and the date. The date is 471. So you can see how early this is. This is one of the very first ones that were written on this. And it gives you a little explanation as to what the Cecil series is. The particular layers. And you'll notice you got a 0 to 7, a 0 to 7, and a 0 to 7. We were allowed 3 different layers of surface textures. And then you had 3 additional layers after that you could put in for subsoil information. So you grouped all of your horizons into layers and then presented that information. And you'll notice that we've got the percent passing as ranges and liquid limit as ranges and the PI as ranges. And you'll notice as you look through here, a lot of this information, very little agronomic, very heavily weighted towards engineering. The only agronomic ones that you actually have are the available water capacity and the pH salinity. And so you can see that we had some early interpretations back then on septic tanks and sewage lagoons. And you just basically hand wrote all of this information out onto this. And so then we had what was called a map unit record. These were 2 different forms. One was for the series interpretation record, and the other was for the map unit record. And this is where you married the information, the soil properties and interpretations for your map unit. So you came in here and you're at Fairfax County, Virginia Soil Survey area, and here's the map unit. Field symbol was 121C3. It was the Appling Gritty Loam. You can see some of this terminology is no longer used. And they changed the publication symbol to AA, and it was done in 1982, Appling Sandy Loam. And it used the interpretation record, the series interpretation record I just showed you of NC0032. You assign the slope, you assign the surface texture, and you assign the flooding phases and any other phases that you may have. You also identified any of the additional symbols that had been used to create this map unit. That was your correlation decisions. And then you had the ability to adjust the layers, and even though the depths appeared on the series interpretation record for the TUD for this particular county, we're going to be using 0 to 7 inches, 7 to 32, and then 32 to 40. And you'll notice that we only went down to 40 inches back then. That was another one of the things that you need to know about the history of soil survey. So the field map unit name, that's what we were using to be able to develop the manuscript. I told you that we used series interpretation records, and you'll notice you only had 3 slots. We're filling one of the slots with the Appling SIR. You had 2 additional slots if you had 2 other major components that were part of that map unit. And then, as I told you, you adjusted the horizon depths on that SIR to be able to match what the typical location was. So those were your 3 edits that you made on this particular document. And then when you married the SIR, or commonly called the SOLS 5 in the 3SD days, and the SOL 6, which was the form that you just saw, what you created was the map unit interpretation record, or MUR. And the MUR data was part of the State Soil Survey database. This was the 1985 database system. And in this one, what I'm using here is I pulled just the Vernon series that's been mapped across the entire area, wherever Vernon was mapped. And what I wanted you to see in this particular presentation is I wanted you to look at the component percentages, and I wanted you to look at the depths. Because you'll notice that everything else was the same. All this data came off the same SOLS 5 ID. But the differences in the data were in the soil depths for the TP and also in the component percentages. And many people are questioning the validity and the purpose of SDJR. This is one of the reasons why we went into SDJR, because there's a lot of overhead here when you have the exact same set of data in tens of counties. What's the purpose of that? They had the same map unit, may have had the same map unit concept, but they definitely have the same set of data. And so the intent was to be able to consolidate these into a single map unit concept as it flowed across the county lines. This is the basis of that decision. As you look at that data, you'll notice that this 3SD data was converted into the NASA's data. And I want you to just take a look at this and see that this data is, in essence, the exact same set of data. There are very little differences when you look across here. Minor differences that are not suitable for argument purposes. And you'll also notice that this is the same set of properties that came off of these SOLS 5. So you can see, based off of the SOLS 5, there were 2 different surface layers for the Vernon series here, 0 to 5. And you'll notice there are clay content. And if you look at the clay contents in the data behind it in the Access Database image there, you can tell the differences between the 2 by just looking at the total clay content. You can see which one was the, I didn't explain this earlier, but the 1-1 and the 1-2 and the 1-3 were your 3 layers. And you can see the differences in 1-1, 1-2. So the current soil databases that we've got We've got the NASAS system, and the NASAS database system includes PET-on PC and Analysis PC. You've also got the official series descriptions, and they're technically not a database. You have the classification database. You have the characterization database. You also have the Sol Data Mart database, and the Sol Data Mart database includes the spatial data. It also includes the staging server database, the Sol Data Warehouse database, the Sol Data Mart database. And the Web Sol Survey is technically a portal. It's not a database. You also have the Sergo database, the MS Access template. And then you also have the U.S. General Soils Map, or the StatsGo database that's residing in NASAS. So when you look at correlation and you look at databases, the first correlation decision that you have to make is where are you going to dig these holes? Because you want to dig these holes that represent the landscape concept that you've built. And you want to determine at that time whether you're going to create, whether you're going to create a complete PET-on description or just a partial PET-on description. So these are the correlation decisions that you're making while you're in the field collecting data. And then you have to discuss what data do we collect. Well, you have PET-on descriptions, and you also have lab data. And I realize that we've done this the same way for eons. We've always collected PET-on data, and those together provide you a set of properties that you're going to populate in the soils database. And using those soil properties, you'll be able to then go in there and create interpretations and predict the behavior of that soil. So where do you get this information at? Well, you're going to go out to the field and you're going to do some digitizing, and I hope that you guys are maintaining the cartographic standards and you're drawing your lines at 1 to 24 and 1 to 12,000. You are allowed to go down to 1 to 12 and 1 to 6 to draw your lines, but do not go any further than that. Your scale at which we produce the map, it controls the mapping at concept. So you are not allowed to exceed that 2 times the publication scale for drawing your lines. It does not do us any improvement by increasing beyond that. So you do your field digitizing, that becomes spatial data. And then you go in there and you collect your data. And you can write your PET-on descriptions out of an auger hole, or you can do a pit and do some sampling. But regardless, that description is put into a database, whether it's in the PET-on PC database, or if it's been sampled, whether you're collecting that information and getting it analyzed and put into the KSSL database. But between those two, you then analyze that information, and from there you populate your NASAS database. And NASAS is a transactional database. It allows you to analyze that data, collect data, analyze it, and then make decisions on it, and change those decisions if necessary before publication. Well, you know, there are a few guys that have done some really wonderful job. Dylan Bodette has created a really nice, useful tool on being able to analyze your PET-on data. And this is a report that's in NASAS, and there's also in R, that you can come in here and take that collection of PET-ons and run this report, and then do a really rapid analysis on whether these are the same PET-ons or not. And just by looking at the PET-ons and looking at the age of these PET-ons, you can see a lot of variability in this soil. It's called Olton. So be aware that there are tools available that allow for rapid analysis. You know, folks like Kevin Godsey have written some really nice reports that allow you to plot this information. And if you have your sand, silt, and clay contents in your PET-on description, which many people do not, you will have the ability to run some of these reports and plot these just to see where the analysis of these textures are. So you can see that all of these points that were collected, and I'm not sure if these are lab data sets that are in the database or if these are actual pedon descriptions that had sand, silt, and clay. But you can take a look at this and you can see that we've got reports that are available for you to be able to analyze these as an image to understand where do they actually fall. And here's another one that Kevin has written that talks about the family class and how this fits into the family class. And then another one of the good ones that he's written shows you the scatter within the chart to be able to take a look at this information and see the diversity of the soils, the properties. And this is the MoCo soil. This is only looking at the A horizons. And you can see the diversity of these A horizons. And you know, as he has written here, the blue polygon is what he considers the minimum and maximum values for the sand. That is based off the population. These are the minimum and maximum values for sand, silt, and clay. And then the yellow is the 2 standard deviations from the mean, and then the green is the 5th and 95th percentile. So you can see that these tools allow you to make some more educated guesses on how to populate your data. And then going back to the Olton, there's a lot of capabilities that we've got in GIS, and these are all the Olton map units that are in the publication database. And then on top of that, here are all the pedons that have been described and looking at the surface textures of those pedons. And of course you have to be careful because you don't know the quality of those surface textures. Granted, most people can estimate within 3% clay content, and once they know their area, they can pretty well identify what the texture class happens to be. But keep in mind, they're not always accurate. And so when you look at this, you can see the scatter, and you can see the heart of the Olton. And this was another SDJR initiative reason, because when you look at this, you know those soils that are basically outside of that heart that goes from New Mexico down southeast into Texas. There are areas up in northeast Panhandle, and there are areas that are down further south that fall outside the home range of the Olton series. And those are all questionable as to whether they are actually Olton or not. And the intent of SDJR was to get you to look at these things and to see, are they or are they not Olton? And if they are Olton, can we group these into an MLRA concept? But also, while you're looking at this, take a look at the variability of the clay loam and the loam and the sandy clay loam. And you can see that there's a great deal of diversity within this one particular series within its particular home range. So early on, one of the issues that we've tried to encourage is the population of certain soil properties based off of known data, not calculating or cheat sheeting. And over the years, pardon me, I collected the soil properties that modelers use, and I looked at it and I analyzed it and I figured out all these different models and what people were using. And those that are in yellow are the soil properties that modelers use consistently. And you'll notice it's the bulk density, the separates, the organic organic matter, pardon me, and then your water content. And the water content was basically to get available water capacity. So you can see the importance of making sure that when you populate based off of your best guess or lab guessed data for bulk density, your particle separates, your organic matter content, and your water content. Don't be using calculations, and if you do use the calculations, go back and verify it. And then data management. Let's move into a new topic. Data management. Point data is captured using POM-PC or NASAS. We've tried and tried and tried, but to use different field tools, but it's basically come down to the point where people still use paper and pencil in the field. And so you can come in and use PET on PC, or you can use NASAS and enter that. We're moving into a form-based data in NASAS that'll most likely eliminate the use of PET on PC in the future. And then you take your soil boundaries. You're either creating your polygon boundaries or else you're modifying your polygon boundaries. And remember, once again, you're mapping at 1 to 12,000 or 1 to 24,000. And so the closest that you can zoom in on your map is 2 times that, which would be 1 to 12 or 1 to 6. Do not go beyond that. And NASA has a myriad of available reports and editing grids that allow you to analyze your data. There's a lot of ways you can analyze your data without even running a report in NASA. You can just look at it in the editor grid. And then you have to build this mapping concept after you've aggregated this data. You've collected it, you've compiled all it and analyzed it, and now you have to make a decision on what is this map unit. And then remember, these soil properties are developed using the component population that's been collected. You're not going to see everything out there. You're most likely only going to see probably less than 1% of the entire population of all the pedons within that map unit. And so you have to be extremely careful about how you're presenting this information to the public as far as soil properties and soil interpretation. One of my mantras that you've heard me or seen me write is that a database lives or dies based on the consistency in which the data is populated. And that is very true. That is one of the reasons why over the past 15 to 20 years we have encouraged people to clean up the database and to make sure that those soil properties are properly populated. There's a report I used to use many years ago just to see how many pedons were being entered into the NASAS. And there were not many pedons. Keep in mind, in the early days, there were no pedons captured in a database. But I think last I've heard is like 600,000 pedons in the database now. We've had a huge increase in the number of pedons being entered into the database in the last few years. And so when you look at some of these, you have to realize that consistency is the key. And so I ran a report and I said, show me all of the particular pedons and how many of those pedons were written into a specific county. And there is a naming nomenclature for the user pedon ID and the user site ID, and it is specific. It uses the 4-digit calendar year. It then uses the state code, the county FIPS code, and it is county, not survey area. And then we allow you, 3 or 4 numbers after that to be able to identify the number of pedons that particular calendar year for that particular county. And what I want you to see is when I ran this report and tried to pull out, you'll notice the number of pedons that do not have the county code embedded into the user site ID or the user pedon ID. And this goes back to a database living or dying based on the consistency. It's dead because people did not follow instruction, and that's instruction that's been available to us since in the 50s. So then compare that to those who did populate properly, and now you can see that KS 149 has 1,096 pedons. KS 155 has 3,637 pedons in that particular county alone. This is how easy it is to be able to analyze it. And yeah, I could have done it using GIS. People say, well, why don't you use GIS? The problem with it is consistency in which the database is populated. And if the latitude and longitude is not populated or some sort of location is not populated, then it does you no good either. So there is a reason for everything that we do. So here is the exact way you're supposed to put the user site ID and the user pedon ID. Notice the S is for a sample, and that's only used if you are sending that off to the KSSL, but it starts with 2005, 2015, whatever. It's that calendar year, it's that state, it's that county FIPS code, and yes, it is county, and then of course the 3 or 4 digits thereafter. And so when you take a look at the data that's been entered, we've modified the screens a little bit in NASAS to be able to make people more aware of the need for this. And you'll see that the user site ID and then the state FIPS and the county and the MLRA that were at one time overlap tables, they're now put into the site table so that you'll populate those as you enter the data. And then you can see that in the PET-ON side, if you copy and paste that user site ID over into the user PET-ON ID, then we have the ability to match very easily between the site and the PET-ON. So here's the PET-ON analysis PC database. Now, I realize not many people are using this, but it was built by Jay Scovlin and is a really useful tool to be able to analyze your PET-ONs in a rapid fashion. It basically established all of the relationships, so you didn't have to wonder how it was done. It had built-in queries. You could write new queries. You could use the access queries, or you could do a form analysis. You could analyze. You could flip it back and forth between ARC and access to be able to analyze your data. And you can also join it with other access databases for further analysis. Now, a lot of this is already kind of antiquated, unfortunately, after 5 years. We've moved on. We've got the lab data now in NASA, so you can actually do your analysis. Some of this stuff in now. So, going back to your correlation in your database, your second correlation decision is where do you draw the boundary, and then what soils are you going to identify within that particular polygon. I'm going to give you a clue. I realize that there's a lot of you out there who want to put down every single soil that there is in the database that you found out there, and it does you no good. Your job is to correlate these soils and to identify similar soils, because when we populate the database, we populate alpha in similar soils and beta in similar soils. Your job is not to go in there and identify the 15 soils that you happen to find in this particular polygon. Your job is to correlate those and identify the soil properties necessary to give the 1, 2, or maybe 3 soils that are substantially different on that particular landform. And that's significant because what you need to understand is 90% of our users only use the first component within the database. And so within the map unit. And so you need to understand that that first component is important, and in no way, shape, or form should there ever be a 40-40 or a 45-45 split on two different components. You make the decision which is the dominant component, because if you don't make the decision, I'm going to accept whichever one comes out first. And it may not be what you wanted, but the point is, make a decision, make one of them dominant, because most of your customers, the vast majority of your customers, are going to use that dominant component, whether you like it or not. So in initial mapping, we have some correlation decisions that we have to make. And whenever we create a new map unit, we have a new map unit symbol, and we have this concept, and we have to track this concept all the way to final correlation. And initially you want to split everything that you find, and then you want to, at the correlation time, lump these into usable map units. Keep in mind you have a minimum size delineation size on 1 to 12 and 1 to 24,000 scale maps, which is basically 1 acre for 1 to 12 and 5 acres for 1 to 24. So you're constantly aggregating and grouping by using all of this analysis that you're doing. You're not going to have 15 components in a map unit. You're going to have 2 or 3 that are substantially different. You're not going to have 50 million different polygons out there. You're going to be lumping these into useful tools that people will be able to do an analysis on when they have to look at your information. And for the initial mapping, the intent was to be able to reverse that correlation all the way back to the original symbols that you put on that map. And that's the reason why we have that correlation table in NASA's. In update mapping, that's a little bit different because now you're reviewing map units that have already been correlated. And in doing so, you have to make decisions on combining these similar map units. And that's what SDJR is all about. You're supposed to be reading the book, you're supposed to be analyzing the data, you're supposed to be making decisions on is this the same map unit concept or not. And if it is, then you're developing a map unit concept based on the MLRA. And in this one, since we're creating new map units and new data map units, by including all of the previous joined map units, we have the ability to track what was the original and then also what was the final decision. So when you start looking at the correlation activities inside the database, there's some tables that you have to be aware of. And the LMAP unit table, legend map unit, links the legend to the map unit. The correlation table links the map unit to its data map unit. And then the component pedon links the component to the pedons that you're using for documenting that particular component. And then when you start looking at documentation, you have the legend map unit history, the legend map unit text, the map unit history, the map unit text, and then all the other text tables that you use for documentation. So here's an example of a linking table, and this is the component pedon. And so you've said this particular component DUI that's in my map unit, I am going to be using these particular data pedons, even though this has a lineage here. You need to be, unfortunately, you need to realize that this is in the component table, component pedon has a lineage. But anyway, these are all of the particular pedons that are being used for that particular component. And then here's an example of that particular data map unit. And I need to go back and look at that. I think I gave you the wrong information in that previous slide. That must have been the correlation table, and then that correlation table then linked to all the DMUs. And then here is one of the data map units that's being used, and you can see that you've got 5 different components, and I will make the assumption that those are 5 distinctly different components within the particular map unit. You remember you're creating DUI and similar soils, so none of these soils should be similar to DUI. And then this is the pedon to component linkage here. I'm now in the component from the data map unit to component pedon, and here is the type location for that DUI for TN107. And then we have the linkage between the map unit and the data map unit, and that goes through the correlation table, and the correlation table is right here. And so you can see that from this particular map unit, here's the correlation, and here's the data map unit record that links to it. And then the last one is linking that map unit to the legend, and here is the legend, and this particular legend has a correlation date of 10/1976. Here's the 2 map units, one of them's correlated, one of them's additional. And for this particular map unit, here is the actual map unit record that corresponds to this legend map unit table. Legend map unit table links the legend to the map unit. So now you got to document some of these correlation decisions. And the intent of the fully reversible correlation was to be able to trace the published map unit symbol all the way back to the original field symbols that were used. It also provided you an ability to give us some sort of documentation as to why and how this particular map unit was correlated. And so the first one you'll see is changing the map unit name. So in the map unit table, you'll go in there and you can populate your text notes to explain why the map unit was changed in the name itself. You can also, in the legend and in the map unit, identify the combination of the map units. For example, if you had an alpha and a beta in an initial survey and you wanted to combine those into an alpha beta complex, then you'd be able to combine the alpha and the beta, leaving the originals preserved, combine them into a new one. And similar, if you were working in an SDJR project where you were combining the alpha silt loams in 3 different counties into a single MLRA map unit concept, and you would be combining those 3 into one. Also, by splitting map units, this goes back into the initial work. Let's say you created a complex or an association that you've chosen to split out into 2 consociations. And then changing the status. You're constantly monitoring the status of the map units and which ones are provisional, which ones are approved, which ones are correlated, and then those correlated that are being correlated out and being moved to additional. That happens in the legend object. And then also if you change the map unit symbol, and in some cases, some states have gone to a statewide symbol. It's very difficult to maintain, but many states do that. And so if you have to change the symbol, make sure you document that as to why it was. So let's go into some of the specifics on each one of these. If you're changing the map unit name, where do you document it? Well, you document in the map unit table. And you'll notice in the map unit history, you can go in there and you've got a choice list for a name change and a correlation kind. And so the previous name was a Dewey-Corrigan complex 15 to 30. And that's what you identify as, I don't know why this particular example doesn't have a change. I don't see a difference in here, but technically there should have been a change there in the name. The historical name would have been what it was, and then of course in the map unit table you would have identified what it is. And if you want to combine map units, we're using an example in an initial survey, and this is the old NASAS. I realize that, but the point is I wanted to show you that in the legend here you've got 2 different map units, and you're going to combine the 4B and the 21B. And so you're going to load up the related map units. You're going to combine these into a new map unit. Now we've got this Woolwine-Clifford complex, and you can use Where's Waldo right there to be able to identify where it's being used at. And so you can see that this is in Tigard County. And the reason why you do that is to make sure it's not impacting survey areas outside of what you're working on. And if you're on an initial, technically it shouldn't. So you go in there and you create that new DMU, and you grab that new DMU, and then from there you paste it into the correlation record for the map unit. And when you're done, you go in there and you check that your new DMU is representative for that particular map unit. And then in essence, you modify the component percentages in order to be able to adjust what you feel is appropriate for that particular map unit now that you've combined. And then you go into the legend table, and you'll notice that in the legend table you have to do a little bit of modification on this. Make sure you take notes. And here's an example in SDJR where they've taken that Dewey silt loam 2 to 6% slope, which is now an MLRA map unit. And here are all the non-MLRA map units that were used and combined into the Dewey silt loam. For status changes, I explained this to you. Provisional is an initial map unit concept. Approved is when the soil data quality specialist has said, yes, this is a viable map unit. We're going to put it on and allow you to continue testing it. Correlated is when it's been signed off and the final correlation is completed for that particular map unit. And then additional is any map unit that has been changed and it's no longer being used. In documenting, you have the legend map unit history to document any changes based off of that particular legend. If you've got any correlation decisions for that specific map unit, regardless of where it's used, you can go into the map unit history and update the documentation for that map unit. Map unit history will go with that map unit regardless of where it's at. Legend map unit is only for that particular legend. Okay, we also include the spatial database as part of our correlation decision, and basically what this does is allow you to have a visual image to be able to identify. And so we can use spatial images to be able to look at soil properties, components, or interpretation. And we have a lot of supporting layers that we can use to be able to assist us in this correlation endeavor. The DEMs, the veg maps. We can use the landscape and landform models, and we can also do analysis on the spatial DEMs to be able to look at hill slope, shading, slope gradients. So in summary, historically we created manuscripts. We wrote them out by hand. But today we use databases and we publish databases. We have spatial and attribute databases. We have multiple databases that include point data, sample and analyzed data, aggregated data, spatial data, aggregated spatial data, such as StatsGo. But it all boils down to the population of the database and the analysis that you've put forth and how you've published that information. So keep in mind, yeah, people can recreate the wheel. Analysis PC is a great example of how a field soil scientist came up with a fantastic idea and it was incorporated into the corporate database structure. We do have that capability. And everybody's trying to do something better, and that's great. But you have to understand everything has to be maintained inside the corporate database structure. Don't go creating things off on your own if you cannot maintain it in the database structure that we've got. This is expensive data, and we cannot afford to have people losing this data, and that's the reason why the corporate database is built. So you have all this documentation in the database, and the intent now is that in the future it'll be available to those that follow you, and that's what you need to understand is the importance of maintaining this in a corporate database system because it's constantly updated.